right, so definite integral is net area. If the function, if little f, right, which is the derivative, and also the integrand, if that changes signs on the interval, then the definite integral represents net area. Right, that is the difference of the areas is indicated below. So if we just integrate and evaluate, then we would find R1 plus the area of R1 plus the area of R3, and then subtracted from that, it'd be the area of R2, or area of R1 minus area of R2 plus area of R3. We'd add the positives and subtract the negatives. And that will happen automatically as we integrate and evaluate. Whether we integrated and evaluated or used a limit of Riemann sums, the negative areas would actually subtract themselves off. We would only be left with the net change. What if we wanted to know all of those areas as areas? Right? Well, then we would have to make that an absolute value, and so then we'd be adding that R2 in. So let's say, so if this f of x represented the velocity, the equation for velocity, for instance, and we integrated and evaluated, in other words, we found the definite integral, regardless of technique we use, we found the definite integral, we would be finding the change in position. What if instead we wanted to know the distance traveled? So we didn't want to subtract off the negative distances. In other words, when we came back the other direction, then we would have to make sure we made that an absolute value, so we would add those in instead, right? So essentially what I'm saying in this slide here is you don't have to worry about whether it's above the x-axis or below the x-axis when we're just looking at net change. And that's what we'll be doing on these ones, looking at net change, right? Net area, if you will. You don't have to worry about what's above and below, because when we evaluate the definite integral, regardless of technique used, that negative just subtracts itself right off. Right? So if f changes signs on the interval and we need to find the total area between the graphs and the x-axis, right, then we're going to have to make sure we add that in rather than subtracting that in. Right? And so one way would be absolute value, and the other way would be to subtract it, because it would be minus a negative. So the area of R1 from A to C would be f of x dx. The area of R2 from C to D, f of x dx, would be a negative area. If we take the opposite of that and add it in instead of subtracting it, then we can add that area in, and then the area of R3 from D to B, f of x dx, would be the R3. So in other words, if what we really want is the actual area, we're going to have to split this up, and we'll see this in a later lesson, but I just want to introduce it now. We're going to have to split this integral up into 3 separate areas and then add that R2 in. In other words, it's going to be negative if we take the opposite of it, right? Then, or the absolute value of it, then we will have our three areas, right? And then it'll be a total area, right? Right now, we're not concerned about total area. We're looking at net change, so we don't have to worry about splitting up the integral, right? When we're going to worry about total, then we're going to split the integral up, right? All right, so for instance here, the definite integral, if we just calculate it out, in the first example, right, A is that positive area under our curve from A to B. In the second example, some of it's below the curve, below the x-axis. So the integral from A to B, the integral of f of x dx evaluated from A to B is going to be that first area, A1, plus that third area, A3, minus the area that's below the x-axis. So it's going to be the area above minus the area below. Right? So that it automatically happens if we don't split the areas up. All right, so for instance here, we're gonna do this one 3 ways again, and the writing is kind of stuck on the picture, but by gosh, that's a really easy area to figure out. All right, so this is the equation x minus 1, right, positive slope, slope of 1, a y-intercept of -1, and we're evaluating it from -1 to 5. Right, so the area below the curve is below the x-axis will be a negative area. Right, so right here at 1, it goes below the x-axis. So the base of that triangle, so notice we can calculate it out as 2 triangles. Right, we have a triangle that's below the x-axis, so it has a negative area. We have a triangle above the x-axis, so it has a positive area. So area would be 1/2 times 2 times 2. So the area of the smaller triangle that's below the x-axis would be -2. Or it has an area of 2, but notice that we're going to subtract it because it's below the x-axis. You can think of it either way. And then the area of the triangle that's above the x-axis, right? So the base of the triangle is 4, the height is 4. So 1/2 times 4 times 4 would be half of 16 or 8. Right? And so we would the integral evaluated geometrically as 2 triangles would be the positive area that's above the x-axis 8 minus the area that's below the x-axis, so -2. So 6 would be the actual integral evaluated from -1 to 5. All right, so now let's see what we get when we find this as a limit of Riemann sums and using what we have learned, integrating and evaluating. So here we're going to do this one as a limit of Riemann sums. And actually, let me just put the little above it. Oops, well, it doesn't want to go. All right. I will just use, right? It really doesn't want to go up there. So I'll move that down here. So we're going to do the limit of the Riemann sums with n subintervals. Right, so let's find our the change in x. That would be 5 minus a -1 over n. So that's 6 over n. Let's find x. We start at the lower limit, -1, plus change in x times j. Substitute x into the function and evaluate. Evaluate, simplify, whatever. Negative, so this would be, so for x, we're going to plug, this is x. So we're going to have -1 plus 6 over nj, and then -1. So, because all of this is x. So that would be -2 plus 6 over n times j. So now let's write that as summing up all those rectangles. So our change in x times sigma, j equals 1 to n, and then time, and we're summing the function that we're summing up, not times, but the function we're summing up, -2 plus 6 over n times j. All right, so now let's split that Riemann sum. Right, so that's going to be 6 over n sigma j equals 1 to n, -2 plus 6 over n sigma j equals 1 to n, 6 over n j. Right, and then we will factor out the coefficients. right, nothing to factor. 6 over n sigma j equals 1 to n negative 2 plus 36 n squared sigma j equals 1 to n j. We'll use power sum for sigma. All right, so this would be 6 over n times negative 2n plus 36 n squared times, come on, n squared over 2 plus n over 2. We'll still simplify this, so the n's will cancel. This is a negative 12 plus. The n squareds will cancel. This would be 18. And then plus the, this would be 18 over n. And now we'll take the limit so this is the limit as n goes to infinity. Negative 12 plus 18 would be 6 plus 18 over n. Of course, that's just the limit of 6 as n goes to infinity is 6. The limit of 18n as n goes to infinity is 0. So 6 plus 0. Just think of it as the horizontal asymptote of 18 over n, right? So that would just be 6, which is what we just got on the last page, right? So what I'm saying is you don't have to worry if you only want net change, if you're just evaluating it. You don't have to worry about whether it's above or below the limit, whatever technique you use, it will take care of itself. The only time you have to worry is if you're finding it as an area. All right, then you have to remember that it's going to be a negative area when it's below the x-axis. So here you do have to subtract the 2, right, when we're calculating it out as area of 2 triangles. However, if we're going to take the limit of the Riemann sums, it's 6. Right? It doesn't matter what's above and what's below. If we're going to integrate and evaluate, so we're going to use the antiderivative here to compute the integral. All right, so we have we're going to integrate the x. Right, so we increase the exponent by 1, divide by the same amount, minus, I'll put equals here, minus, increase the exponent by 1, so it'd be minus an x, and divide by 1 is still minus an x. And we're evaluating that from negative 1 to 5. We'll plug in the 5, and then we'll subtract and plug in the 1. Oh. And if we're evaluating using an integral, it's going to be f of a, big F, our antiderivative, evaluated at, what happened to this? It should be f, we lost part of it. Our antiderivative evaluated at b, I think there was a b in there at one point, and it moved, and it got erased. And then our antiderivative evaluated at a. All right, so we have 5 squared divided by 2 minus 5. Put that in parentheses. And then, oops, oh my goodness. My hand is going faster than my brain here. And then minus, we're going to plug in the negative 1. And the negative 1 is squared because all of x is squared. So negative 1 squared over 2 minus negative 1. All right, so that's going to be 25 halves minus 5. And that's all together. And then minus, this would be now a positive 1/2 plus 1. All right, so 25 halves minus, so that would be 10 halves. Minus, this would be 1/2 plus 1, that's going to be 3 halves. All right, so 25 halves minus 10 halves is going to be 15 halves. Minus 3 halves is 12 halves, which is 6. Right? So we don't have to worry about. So if you want just the net amount, the negative areas are subtracted off automatically, all right, when you're evaluating. You don't have to worry about splitting up the integral. If you want total area, you have to split the integral into two integrals where the sign changes and make it absolute value, all right? So just remember that. And you can add that to your notes. It's not going to occur in this lesson, but in a later lesson, we'll be worrying about splitting it. Right now, just going to calculate it. All right, so we'll calculate this one. And did I leave a? I think I'm just going to do, this is going to be the last one on here. And I am just going to use our, matter of fact, I could only integrate and evaluate. Because what on earth would I do with that? We don't have a power sum rule for that. If that weren't there, I could do it both ways. I got nothing but evaluate and integrate and evaluate. All right, so let's do that. All right, so I'm going to just write the problem. All right, so we are integrating 2x minus 1 over x plus 1 dx on the interval from 1 to 5. Integrate 2x, that would be 2x squared divided by 2. Whose derivative is 1 over x? It's natural logs. If this were an indefinite integral, we would want to put absolute value signs around it because that x has got to be positive. Because it's a definite integral and we're going to plug in numbers for it, doesn't make any difference. And then plus, this is going to be plus x. That's whose derivative is 1. And we're going to evaluate all of that on the interval from 1 to 5. So we'll plug in the 5. So we have 2 times 5 squared. Why do I have 2 over 2? Why don't we just make that x squared? Let me just simplify first. Natural log of x plus x now evaluated from 1 to 5. So that would be, in parentheses, I'm going to plug in the 5 squared minus 5 plus 5. And then minus, now plug in the 1s. 1 squared minus natural log 1 plus 1. So that is 25 minus natural log of 5 plus 5. Can't do much with the natural log of 5 there. And then minus, this would be 1. Natural log of 1 is 0. What do you have to raise e to get 1? 0. Plus 1. So that's going to be 30. And actually at this point, I'll leave the parentheses on for one more moment. 30 minus natural log of 5. And then minus, that would be 2. So that would be 30 minus 2, which is 28 minus the natural log of 5. Yeah, we don't get those with the limit of, we don't get natural logs with the limit of Riemann sums. And that's our final answer. And it's also the end of this video. Oops, and we got a random keyboard in there. So thanks for watching. We're going to look at some properties of integrals in the next video. Bye for now.